I want to take a moment to talk about the computational properties of this action potential that we just outlined. So we have input into our neuron from these dendritic branches. Other neurons synapse onto them. They depolarize the areas locally, and that depolarization can build and travel down the dendrites into the cell body. The depolarization that triggers an action potential has to be right here at our axon hillock. And so this mechanism, the cell body and the dendritic branches, they act to sum all of the positive inhibitory or excitatory activation that the cell is getting. And if that activation causes a net depolarization that goes to the threshold, triggering that all or nothing spike, then it will fire. So it is taking input, it's summing it. If it activates a threshold, if it goes below that threshold, it then passes on information to the next neuron. And this, as we'll see, will turn out to be very important when we look at neural networks. So let's get back to where we were now. So we have membrane depolarization. At the same time, we're having this membrane depolarization. It's both decreasing the electrical gradient, so there's less of a difference in charge from inside to outside, and it's decreasing the chemical gradient for sodium. There's more sodium inside than there was before. The difference in concentrations isn't as great. And these things slow sodium influx a bit, but they're not enough to halt this depolarization. So what happens then? Well, as we depolarize, a period of time goes by, a brief period of time, and that depolarization now triggers the opening of voltage-sensitive potassium channels. It also will cause the inactivation gates in the sodium channels to close. The sodium channels aren't completely closed, they're just inactivated. Now, the high concentration of potassium inside the cell, remember 20 times more potassium inside than outside, has this concentration gradient, chemical gradient, that causes potassium efflux. And together with our sodium-potassium pumps, we work towards a repolarization of the cell during the refractory period. So membrane depolarization triggers increased potassium conductance because it opens up these voltage-sensitive potassium channels. It inactivates the sodium influx. The sodium-potassium channels kick in. We get potassium efflux, positive ions leaving the cell again, and that works to repolarize the membrane. We can look at the membrane as action potentials travel down and look at these different steps. So once we get that specific action potential here, right, our sodium channels open up, we get this massive depolarization, and oftentimes they'll show it as peaking at about positive 40 megavolts. Right? So from negative 65 to positive 40 change in polarity. Now, about the time we start to hit this peak, that causes our potassium channels to open, our sodium gates become inactivated, and we start to repolarize down towards resting potential. We enter into what's called the absolute refractory period. These mechanisms actually overshoot reestablishing resting potential. They go below that, and that's called the absolute refractory period, whether the membrane is hyperpolarized, that is, it's greater than its resting potential. Negative 80 is often a figure you hear. And then it slowly normalizes again, at which point we can have another action potential traveling down this area of our axon. And so we have this train of action potentials going down. The interval between the potential action potentials is about 6.5 milliseconds. So we can have one every 6.5 milliseconds traveling down this axon at a velocity of about 25 meters a second. However, the conduction speed of an action potential down an axon is determined by a number of different factors. For one, how far away a localized depolarization at one place on an axon is from the next spot where we have a potential polarization we want to occur. And so this is often called local current. And it's determined by two things: the electrical resistance of the membrane, its external resistance, and what is in the axon, in its internal resistance. External resistance is affected by the number of channels in an area on the axon membrane. So if you don't have a lot of channels in an area, then it will have to have a greater depolarization in order to trigger a depolarization that is farther away or fueled by fewer channels. Internal resistance is largely determined by the diameter of the axon. So there are kind of two solutions for faster conduction. Generally, larger diameter axons have low internal resistance and can conduct faster. And this is the strategy used by many invertebrates. Now, in contrast to that, most mammalian brains rely primarily on this mechanism of glial cells encasing the axons, right? Myelination, and thereby decreasing the channels and increasing the reach of the local current. So in myelinated axons, depolarization sort of metaphorically hop from one node of Renvier to another, right? And that can potentially increase conduction speed by as much as 10 times. And this is called saltatory conduction. Now, how does it work? Well, if we encase an area, say this is an area that we've encased with a glial cell, all right? Now, the internal resistance here, when sodium influx comes in, it's going to come in. There's not going to be any transport in or out here. It's going to bump against these and just sort of push things down. And as it pushes them down, it'll push down sodium, and it'll cause a change in polarity at the other side of our node of Renvier, which will then trigger the voltage activated sodium channels to open up at that node. And so we get node pushing ions to the next node, pushing ions to the next node, and so on.